Hello everyone, welcome to the midterm presentation of our EE675 course project. My name is Rajvardhan Verma and I will be presenting the project slides on behalf of my team members Rohit and Saurabh. The topic of research of our project is best term identification in cost-aware cascading bandits. But what do we understand by the term cascading bandits? So basically the fundamental concept of the cascading bandit problem is to focus on recommending the k most attractive items from a list of L ground items. The cascading bandits follow a sequential nature where each choice affects future decisions and rewards, reflecting real world scenarios where choices are interdependent. I also want to highlight the unique aspect of the cascading bandit problem, which is the complex reward structure. Unlike traditional bandit problems, rewards in this context are influenced by the entire sequence of choices, adding layers of complexity to the decision making process. Now let us talk about the use case of cascading bandits. Now we can find the application of cascading bandits in the area of recommendation systems, where users evaluate items one by one, clicking on those they find attractive and moving to the next if they are not interested. So the primary goal here is to learn the click probabilities of items over time to enhance the efficacy of the recommendation list. Here we present an example of the cascading bandit setting. Now let us suppose that we have 6 different fruits. So the length of the ground list will be 6. Now consider that the RL agent recommends 3 fruits to the user, which are strawberry, mango and apple. So the recommended set is of size 3. These items will be displayed sequentially to the user. When the first fruit is presented to the user, which is strawberry, and if it dislikes it, then its weight will be assigned as 0. This weight is also equal to the click probability of the item. And when a second fruit, that is mango, is presented to the user, and if he likes it, its click probability will be assigned as 1. And hence the value of k dash will be 2. That is, we have observed 2 items of the recommended set and 1 item is still left unobserved. Now this whole thing will be sent as a feedback to the RL agent and the click probabilities will be updated accordingly. So this is how the cascading bandit settings work. Now we move on to the cost aware cascading bandit setup, which is the main theme of our analysis. So what are cost aware cascading bandits? Cost aware cascading bandits are an important variant of the general multi-armed bandit problem. Unlike traditional bandits, where the focus is solely on maximizing rewards, cost aware cascading bandits, on the other hand, also consider the costs associated with each action. This adds complexity to the problem as decision makers aim to balancing maximizing rewards and minimizing costs for every action. Now let us break down the problem into 2 steps. Firstly, the decision makers receive rewards for advancing to the next stage, but they also incur a cost for taking actions. The overarching objective is to maximize the total reward while simultaneously minimizing the total cost, which is incurred through multiple stages. Now, this dynamic optimization problem requires balancing the trade off between rewards and costs at each decision point. Secondly, we have the cascading effect in cost aware cascading bandits, where decisions at each stage are influenced by the outcomes of previous stages. Now, if the reward is below a certain threshold or the cost is too high, the decision maker may choose not to proceed with it, which is okay. Balancing rewards and costs across multiple stages presents a significant challenge, requiring adaptations of traditional bandit algorithms. Now, additionally, the applications of cost aware cascading bandits span various domains, including online advertising, recommendation systems, and healthcare, which highlights the importance of considering both rewards and costs in our decision making processes. Now, let us discuss the problem setup of cost aware cascading bandits briefly. We are given a set of k items, each with 2 states 0 and 1, which are basically evolving out of a Bernoulli random variable. The learning agent chooses an ordered list of items in each step, which examines them sequentially until a stopping condition is met. The reward mechanism grants a reward of 1 if any examined item has state 1, otherwise, the reward is considered as 0. Additionally, each item examination incurs a random cost, which is unknown to the user, and the net reward function is calculated as the reward obtained minus the total examination costs, which are incurred before we stop. Now, since we can acknowledge the complexities which are introduced by the cost considerations in selecting the most rewarding arm efficiently, our study now focuses on determining the number of samples which are required for a specific algorithm tailored for the cost-aware cascading bandit problem. Understanding the sample requirements is crucial for both assessing the algorithm's feasibility and adaptability. The primary goal of our research is to identify the number of samples needed by the selected cost-aware cascading bandit algorithm, which is a upper confidence bound, which is a UCB based algorithm, to identify the best arm with high probability. Thus, we will be able to adapt the bandit setting for a variety of applications. Following our project's problem statement, I will now introduce the base reference research paper titled Best Arm Identification is Cascading Bandits. Now, this paper serves as a foundational reference for our study and provides valuable insights into the best arm identification problem within the Cascading Bandits framework. This paper analyzes an algorithm called Cascade BAI, where BAI stands for Best Arm Identification. Therefore, Cascade BAI is designed to identify the best set of K items, which are called ARM, within the framework of Cascading Bandits. The paper also discusses the derivation of an upper bound on the time complexity of Cascade BAI by estimating the available feedback at each step probabilistically. Additionally, a lower bound on the time complexity of any best arm identification algorithm in Cascading Bandits is established to demonstrate the optimality of Cascade BAI algorithm in certain scenarios. The efficacy of Cascade BAI and the tightness of its upper bound on the time complexity are further validated through extensive numerical simulations. In the Cascade BAI algorithm, the paper delves further into the fixed confidence setting within the Cascading Bandits framework, particularly addressing the statistical dependencies between feedback and time steps. This setup entails selecting the most promising items from a list of L ground items, which are each associated with a click probability. This click probability Wi belongs to the set 0 to 1. At each time step t, the agent selects an arm of k items from the ground items. This arm is represented as st, which is a set of k different items belonging to set L at a particular time t. This indicates the items that are chosen for examination. Now, the feedback OT from the user is critical. This feedback is in terms of a vector where each entry corresponds to an item in the arm. Now, if a click is observed, then the value of that particular item will be 1. If a click is not observed, the value will be 0, and if that item is left unobserved, its value will be star. This whole information will be sent as a vector to the agent. Now, continuing further with the problem setup, items are deemed to be optimal if their click probability exceeds or equals to the kth highest click probability. Now, to ensure that only k optimal items are selected, it is assumed that the click probability of the kth item, which is wk, is greater than the click probability of the k plus 1th item, which is wk plus 1. This condition defines the set K as a set of items which belong to the range L whose click probability is greater than or equal to Wk. Additionally, the concept of epsilon optimality is introduced, where an item is considered epsilon optimal if its click probability is close to the kth highest click probability, which is within a tolerance of epsilon. Then, the paper explained the components of the algorithm in the Cascade BAI framework. The algorithm takes three inputs parameters for our analysis. First is the sampling rule. Sampling rule is responsible for determining which arm to pull at each time step. It takes into account previous observations and algorithmic specific criteria to make informed decisions. Next one is the stopping rule, TPI, which decides when to terminate the algorithm. Now, this decision is typically based on reaching a predefined confidence level or after a certain number of iterations to ensure computational efficiency. And the last one is the recommendation rule, phi-pi. This selects the arm S-pi to choose the optimal arm eventually. This selection is often based on the most frequently sampled arm or other criteria as determined by the algorithm. Now, the primary goal of our algorithm is to achieve a PAC, which is probably approximately correct solution, ensuring both the expected number of pulls and the number of pulls even are smaller within high probability. The Cascade BAI algorithm follows the idea to obtain the lower and upper confidence bounds, which is LCB and UCB, to know whether an item is optimal or not. First, the algorithm puts or rather defines the risk parameter delta, the tolerance epsilon, and the size of the arm, which is k. We initialize the time step as t equal to 1 initially and let dt denote the survival set at time t. We keep an item in dt to know whether it is optimal or not. And at is the accept set. We move an item from dt to at if we identify that item as optimal. And rt is the reject set. We move an item from dt to rt if we identify the item as suboptimal. T of I at time t denotes the number of observations by the time step t. Weight of I at a particular time t denotes the empirical mean of item I at that time. These two parameters are set as 0 in the beginning. Now we run a while loop till dt is not empty and the number of items in at is less than k and the number of items in rt is less than l minus k. We sort the items in dt according to the number of previous observations, T of I. If the number of items in dt set is greater than equal to k, then we pull an arm st with k optimal items, else we pull another arm st that consists all the items of set dt and an item s-t, where s-t is any k minus dt subset of the union of A and R. After that, we observe the click KT. Now for each item I belonging to set dt, if Wi is observed, we update the weight of that item accordingly. Otherwise, the weight remains unchanged and we update KT equals to K minus of AT. Further, we calculate the upper and lower confidence bounds for each item I belonging to set dt. We then find the items in dt that have the kth and k plus 1th largest empirical mean, and according to this we update the three sets, which are the action set, reject set and survival set. Now if the number of items in set at equals to k, we output at, otherwise we output the first k items that entered at. Eventually we output an optimal arm with probability 1 minus delta. So this was our algorithm on Cascade BAI. In this slide, I have shown some of the important results which are given in the research paper. The first one is the upper bound on the time complexity, which is given in two special cases. In the first case, all click probabilities are taken to be small. that is, they are not greater than 1 by k. In the next case, all probabilities are large, that is, they are at least 1 by 2, that is half, and a bound is created based on this. We use delta I to denote the gap between two click probabilities and use sigma to denote the permutation that arranges the items in any order with given gap delta I. So this is how we have upper bounded the time complexity of cascade BI algorithm in certain special cases. In addition to the upper bound defined in the previous slide, we also derive an informative theoretical lower bound on the optimal time complexity, which is over all the best arm identification algorithms for cascading bandits. We use mu k to denote the upper bound of the expected number of observations per time step. We also use d of mn to denote the KL divergence between the click probabilities of items m and n. Now I will briefly explain the other research papers that we have studied for the better understanding of our topic. The next research paper is titled as Cost-Aware Best Arm Identification, which delves into the challenging problem of integrating cost considerations into the best arm identification process for a multi-armed bandit setup. Traditionally, multi-arm bandit algorithms focus solely on maximizing rewards without considering the associated costs. However, in real-world scenarios such as product development or online advertising, it is essential to balance rewards with costs. The objective of this paper is to address the cost-aware best arm identification problem, in short CABAI, which involves the identification of arm with the highest expected reward while taking into account the associated costs. This problem is crucial for decision making in various domains where resources are limited and efficient allocation is needed. This problem tackles several issues like sampling arms during testing with unknown costs. This involves determining which arms to sample for testing while considering that the costs associated with each arm may not be known in advance. Next issue is identifying the best arm. Now, determining when to stop sampling and declare an arm as the best arm based on the observed rewards and costs. And the last one is selecting the arm for implementation. Now, once the best arm is identified, deciding whether to implement it or continue sampling to gather more information. This issue is also addressed in this research work. The algorithm proposed in this paper addresses all these key questions to obtain the best arm while considering both rewards and costs. It likely involves sophisticated strategies for balancing exploration, which is sampling, and exploitation, which is decision making, to achieve the optimal trade off between maximizing rewards and minimizing costs. The following novel contributions are made in this research paper. Firstly, this introduces the CABI problem, which emphasizes its differences from traditional best arm identification problems. CABI integrates heterogeneous arm costs into the decision making process, which is crucial for real world applications where costs play a significant role. The paper also demonstrates that traditional BAI, that is best arm identification algorithms, are suboptimal for CABAI due to neglecting heterogeneous arm costs. This highlights the importance of developing specialized algorithms that explicitly consider both rewards and costs. Now, two algorithms are proposed in this regard. First is the CTS algorithm that matches a non-asymptotic lower bound on cumulative cost and reward. It aims to achieve an optimal balance between maximizing rewards and minimizing costs in CABAI scenarios. Now, the next one is the CO algorithm. The CO is a low complexity algorithm which is based on Chernoff overlap principle. It shows promising empirical and theoretical results offering a practical solution for CABI problem setups. Now let us define the CTAS algorithm step by step. In the beginning, each arm is pulled once to gather initial observations of rewards and costs. After that, in each time step, the algorithm computes the forced exploration and the optimal proportion of arms to sample based on the current rewards and costs. Now, if the forced exploration set is non-empty, the algorithm selects the least pulled arm from this set to ensure exploration. Else, if the forced exploration set is empty, the algorithm chooses the arm with the largest deficit in reward cost ratio. This balances exploration and exploitation. The algorithm employs a stopping rule which is based on the cumulative cost ZT to terminate the process once a certain condition is met. Now, this ensures that the cumulative cost does not exceed a predefined threshold. Finally, the decision rule returns the arm with the highest estimated reward based on the observations gathered during the sampling process. In conclusion, the proposed research paper introduces the CABI problem, highlighting the importance of integrating cost considerations into best term identification for the multi-banded setup. It provides a new lower bound for CABI and proposes an asymptotically optimal cost adapted best term identification algorithm. Now, this algorithm aims to efficiently identify the arm with the highest reward while considering the associated costs. Additionally, the paper introduced a low complexity algorithm with promising empirical results. This algorithm offers a practical solution for addressing the CABI problem in resource constrained environments. Also, as a future direction, the paper suggests exploring how the proposed algorithm can be adapted to the regret setting, either in the cost adapt setting or as an empirical total cost algorithm, to carefully choose costs. Now let us move to the third paper, which is titled Cost Aware Cascading Bandit. This paper focuses on introducing the cost aware cascading bandit framework, aiming to optimize the expected net reward under different cost settings. The primary objective is to develop algorithms that efficiently balance exploration and exploitation to maximize cumulative rewards while considering the costs. The paper starts by presenting the system model of the cost aware cascading bandit framework. It then delves into scenarios with known and unknown instantaneous costs. Particularly, it explores the case of unknown immediate reward in the optimal offline policy, where the cost of pulling each arm is unknown until it is pulled. The learner needs to learn the statistics of rewards and costs through observed arm states and costs. A few assumptions have been made in this paper regarding the CACB framework. Let's discuss each of them. The first assumption states that the true reward distribution parameter theta I for each arm I is not equal to its associated cost, which is Ci. In other words, there is a distinction between the reward characteristics and cost characteristics of each arm. Further, we assume that the cost of pulling each arm is greater than a positive constant epsilon. This condition is necessary to prevent division by zero or error and maintain a well-defined framework. Under these assumptions, the paper presents the optimal offline policy named the unit cost ranking with threshold 1. This policy ranks the expected reward normalized by the average cost and compares it against a threshold. It's worth noting that the violation of the first assumption would lead to a non-unique optimal offline policy, highlighting the importance of these assumptions in the framework. The expected net reward structure in the CACB framework is more intricate as compared to the traditional multi-arm bandit problems or standard cascading models. This complexity arises from the integration of cost considerations into the reward optimization process. The paper provides a detailed formulation of the expected net reward structure. This formulation likely includes considerations such as the expected rewards from pulling each arm and the associated costs and the net reward obtained by balancing rewards and costs. This will help us to gain insights into the dynamics of decision making in the cost aware cascading bandit framework. The given paper defines a theorem which provides insights into the arrangement of arm indices under the optimal offline policy in our CACB framework. The theorem suggests that arranging the arm indices in such a way that the theta I to Ci ratio is in the descending order. Here theta I represents the expected reward from pulling arm I and Ci represents the associated cost with it. This arrangement ensures that arms with higher reward cost ratios are prioritized. Under the optimal offline policy, denoted as I star, the arm indices are an ordered set of all the optimal L items. This ordered list represents the optimal sequence of arms to pull for maximizing the expected net reward. The theorem shows that ranking the arms based on the ratio of theta I to Ci and including all those with theta I by Ci ratio greater than 1 in I star achieves a balanced trade-off. This balance maximizes the expected net reward from the current arm while also maximizing the cumulative net reward from the remaining arms in I star if the current arm has state 0. Now let us look at the UCB based online algorithm step by step. The algorithm takes two inputs, epsilon and alpha. These parameters are crucial for determining the exploration exploitation trade-off and the confidence levels in estimating arm parameters. The algorithm begins by initializing the process. All arms in the set K are pulled once and their states and costs are observed. This step ensures that the algorithm has initial information about the arms to start the decision making process. After that, it enters a loop where it iteratively updates and evaluates each arm. This loop continues until a specified condition is met or a break condition occurs. For each arm, the algorithm calculates upper and lower confidence bounds, that is UIT and LIT respectively, which is based on the observed states and costs. These bounds represent the uncertainty around the estimated reward cost ratios for each arm. If the ratio of U of IT to L of IT exceeds 1, indicating that the upper bound on the reward cost ratio is higher than the lower bound, the arm is added to the set IT. This set contains arms with potentially high reward cost ratios, which makes them candidates for exploration. Now, next the arms in IT are then ranked in descending order of their U of IT to L of IT ratio. This ranking ensures that the arms with higher potential reward cost ratios are given priority for exploration. The algorithm sequentially pulls the arms in this ranked set until it observes a successful pull. That is, x of IT at any time t is equal to 1 for a particular item I. This step involves exploring arms by pulling them and observing their outcomes. After pulling an arm, the algorithm updates the estimates for the arms in the set I tilde t based on the observed outcomes. This step ensures that the algorithm continuously learns and adapts its decisions based on new information. This is how this algorithm sequentially pulls arm to gather information and maximize cumulative rewards while considering the costs. Now, to conclude the discussion, in this research paper, we studied the CCB model by taking into account the cost of pulling arms in the Cascading Bandits framework. We have considered two different scenarios depending on the availability of the immediate costs. For each scenario, we first explicitly characterized the optimal offline policy and then developed a UCB based algorithm for the online setting. We analyzed the regret behavior of the proposed CCUCB and CCUCB2 algorithms and showed that they are order optimal. An extension to incorporate the endgame failure was also studied. Experiments using both synthetic data and real world data were carried out to evaluate the algorithms in this research paper. Now we will move on to the final section of our presentation where I will discuss potential future research directions that could lead us to the solution of our original problem statement. As we have seen in the cost-aware cascading bandits variant, the objective is not only to identify the best arm, but also to consider the cost associated with each arm. Now this adds another layer of complexity to the problem, as till now we aim to both maximize the reward and minimize the cost incurred during the exploration process. To answer this question of how many samples are required to identify the best arm with high probability in the cost-aware cascading bandit settings, a thorough analysis is necessary. This analysis would likely need to be similar to that conducted in the original cascading bandits problem, but would need to incorporate the cost aspect into the analysis. Now, to tackle this complex problem effectively, we plan further to break it down into smaller steps. By breaking down the problem into smaller components, we can systematically address each aspect and develop strategies to optimize both reward and cost considerations into the decision making process. To start with the next half of our project, we will first conduct an in-depth review of the existing literature on regret analysis for the bandit algorithm setting, with a particular focus on the UCB based algorithms. Our review will also encompass studies that incorporate cost considerations into the bandit algorithms. We aim to identify any related work that addresses regrets caused by pulling arms in the wrong order or considers both reward and cost aspects simultaneously. Our next step involves decomposing the regret into two components. The first one is a regret caused by pulling arms with low rewards, that is, theta I is less than Ci for a particular item I. And the second component is the regret caused by pulling arms in the wrong order. Now we plan to develop mathematical formulations for each component of regret to understand their individual contributions and how they interplay in the decision making process. After that, we plan to derive theoretical bounds on each component of regret separately. This analysis will consider the specific characteristics of the CCUCB algorithm and how it interacts with the reward and the cost aspects of the decision making process. Additionally, we will investigate the effect of the UCB padding term U of IT and the other parameters on the regret bounds. Understanding how these parameters impact our regret will provide valuable insights into the algorithm and hence will increase its performance, and this will guide parameter tuning strategies. After doing all the theoretical analysis, there comes our individual efforts for this project. Our main contribution will be in addressing the technical challenges that are associated with analyzing regret caused by pulling arms in the wrong order. This aspect of regret requires novel insights and approaches as it adds complexity to the decision making process. We will try to explore new theoretical frameworks or extend the existing ones to handle this aspect of regret within the context of bandit algorithms. So this is how we aim to move further with this project. Thank you all for your attention and interest in our presentation.